Hello everyone, welcome to this session. In the previous sessions, we talked about the model training process. So in this session and the next one, we will talk about more on the model evaluation. So last week, we have said in the supervised learning, the data set can be partitioned into the training set and the test sets. So for the training set, we use them to train the machine learning model. Well, for the test set, what we use is that as a benchmark to evaluate if the trained model works well or not. So to evaluate a trained model works well or not, we introduced a prediction error and we made an example of a linear regression. So in this session, we will go deeper into the prediction error. We will analyze how the prediction error is composed of and how to reduce it as best as we can. So we can see here, this is a formula, the error equals to bias to the power of 2 and plus the variance plus the noise. So from this one, we can see there are 3 components of the total error, the bias, the variance, and the noise. So let's see the easiest one, so that is noise. So noise is not something that we can reduce. This is a natural difference between the model that we build and the real data, right? So we can't reduce noise by creating good models. That's why we just have to leave it there. But what we can do is to improve the bias and the variance. So let's see the definition of them. Then we will explain it in more detail. So bias, we said, is the difference between the average prediction of the model and the correct value, right? The real value, the predicted value, the average difference of that. We call it the bias. So bias is affected by 2 factors. First, the model itself, and the second is the training. So for example, the X and Y, the general model is cubic and the relation is cubic. But I use a linear model to do the regression. Clearly, the result won't be good. So this is a kind of bias. So for example, in the training, the gradient descent method maybe needs to run 100 iterations, but I stopped it in 20 iterations. So the model is not well trained. So this again leads to bias. Right? So variance is different. So variance, the definition is a variability of model prediction for a given data point. So this one is highly related to training, and we will provide more explanation and examples later in this session. So let's first see the bias. Right. So models with high bias, so this kind of model, when we see both the training data and the test data, the error is large. Right. So this could be caused of the strong assumption on training data. Just as the example I have said, maybe a cubic relation, I use a linear model. So this is the assumptions is too strong on the training data. The second is we call it underfitting. So underfitting is an important concept in machine learning. So what is underfitting? So underfitting refers to a machine learning model, and this model, both in terms of the training data and new data or test data or other data, right? So neither it can model neither of them well. So this is called underfitting. So let's see some examples, right? So let's see if we do regression. For example, these points, the good fitting is here, linear fitting, good Y is here. But let's see what kind of figure is underfitting. So we can see it's here, right? So we can see this one just doesn't come to a good fitting, so it's a bit far from it. So this one we call it underfitting. So we can see for this training data, the difference is large, the error is large. If we put new data here, the error could be again large, right? So this is called underfitting for regression. If we say classification, maybe this is a good fitting. So we can see the 2 different categories are classified. Only 1 or 2, are misclassified like this. So for underfitting is what? So maybe this is an underfitting, right? So we can see many of them are fitted into the wrong categories. So this is in terms of classification. So we can see this is a underfitted model, machine learning model, right? So for underfitting, how to detect it? This is quite obvious, right? Because when we see the training data, the test data, we will find both of them show us poor performance. When we saw there is underfitting, so how to improve it? How to improve the model? So avoidance, there are several tips. First, if we use too strong assumptions to the data set, so we need to change to other machine learning algorithms, right? So for example, maybe a linear regression is not good enough, then I change it to maybe neural networks, right? Or KNN, we change to others. So this is an avoidance of underfitting. So in this case, it means that the machine learning algorithm that you use is not fit for this data set. So then try others, right? The second is that we can increase the duration of training, because sometimes underfitting is caused by the machine learning model is not trained well. So we can increase the length of the training to make it trained well, give it more opportunity to improve the loss function, right? So these are the methods to avoid underfitting. Then we can talk about the second key concept, variance, right? Variance that we can consider. Supervised learning will map input to output. So ideally, if the exact relation between the input and output, they are caught by the machine learning model. So no matter using which kind of training data, if I change a set of training data, if the model is good enough, it should show me the same or very similar predicted target function, right? Value of the target function. But in reality, the model can't be so ideal. So if I change a set of training data, the target function value predicted one maybe changed. So the variance that is amount that estimate of the target function change. So when different training data is used, right? So normally the machine learning models showing high variance that they often have good performance in the training data, but for the test data, the error is large, right? So this can often is a result from the machine learning algorithm to catch the random noise in the training data set. So we wanted to catch the general tendency, but instead it catch the random noise in the data set. So that one, we call it overfitting. So overfitting is again a very important concept in machine learning. So now let's see some examples. So intuitively, we can think machine learning is that what? The models the training data too well, right? It catch every details, but that's not what we want. So we can see for regression, this is a good fitting. What will be the overfitting? So we can see it's like this, right? It catch every point well. So we can see in the training set, the error could be very low, right? Compared to the good fitting. But this one doesn't have generality. So for example, if we put a point here, using the good fitting, it should appear around here, right? But for this one, it could around here, right? So this doesn't have generality. If we use new point to do it, the error could be large. But the new point, using the regression to predict the value of new points is what we want. So the overfitting model couldn't be used. So let's see the classification. This is a good classification, right? Good fitting. The overfitting is what? You can see here. It catches every detail, but this one doesn't have generality. So if for points here, if we put a new point, it could classify it wrong, right? So this is some overfitting. Then we want to avoid overfitting. So how to detect and prevent that? For detection, so often if you find the prediction error to the test set is much higher than that of the training set, then your model is most likely to be overfitted, right? Because it learn the training set well, but doesn't have the ability to generalize to new points. So how to avoid it? So there are some methods. First, we can increase the number of training data by providing more information to the learning machine. Right. The second, we can remove the irrelevant or not important features to avoid the machine learning to learn them, cause it to be overfitted. So we will introduce how to remove irrelevant features in the next specialization, the advanced techniques. Another method is we call it early stopping. So when we are optimizing the loss function using the training side, the loss function always goes up, always improve. But for the test side, it doesn't work like this. Why is overfitted? When the model is overfitted, the result on the test side will be improved and may become worse, right? So there must be a correct point to stop the optimizing the loss function to avoid overfitting. And how to identify this point, we will explain it in the lectures in the future weeks. Besides, we have a measurement, we call it a k-fold cross-validation. So this method can help us to reduce overfitting. So some of the overfitting are caused by not appropriate hyperparameters, right? So using this one, the k-fold cross-validation, we can get an objective evaluation of the model so as to compare different models and select the appropriate hyperparameters, right? So let's see how k-fold cross-validation works. So now I have a data set. I divide it into 5 folds. So we can say fold 1 to fold 5. So in the first iteration, I use fold 1 as a test data set and the fold 2 to fold 5 as a training data set. Then from this one, I train a model, then I test with this one. Iteration 2, I shuffle them. Now this one becomes a test data set, and all the others are training set. So we iteratively do this process until the 5th iteration. So what we can see, the fold 1 to fold 4 are the training set, and fold 5 is the test set. So in this way, we can get the 5 evaluation scores or prediction error. Then they can be averaged to evaluate the model, considering a certain model type and a certain hyperparameters. So how can we estimate the bias and variance when using the k-fold cross-validation? So we can do like that. So now we get k different estimated prediction error. We name that to E1 to EK. So the bias, we can estimate them by the average of them. So we can see this is a formula. And the variance, we can estimate it by the standard deviation of them. So we can see this is a formula. So in this way, we can have an objective judgment of the model. So then I can see which hyperparameter to use, and I can also compare different machine learning models. Okay, so that's all for this session. Thank you very much, Mehmet.